All right, talking about the diagnosis. Up to date, there are several Liberibacter candidates in this group, genus group. There's 6 species have been reported. The one of a subspecies. So all the 7 candidate Liberibacter have been identified, and a group as a Liberibacter genus. Among these 7, 4 of them are pathogenic. That means it's causing the disease, and 3 of them are associated with citrus HLB, and then the other one is causing the potato zebra chip disease. So these bacteria have been difficult to study because it's a fastidial nature and it cannot be cultured even today. So that the very limited information and they're variable. So several years ago, I think starting 2007, we started taking the effort to do the genome project to get the whole genome sequencing of the Liberibacter. We first completed genome for Asiatica for the U.S. Florida strain, and follow up by completed genome in 2009 on the solanacearum that's causing a potato zebra chip disease. And we continue the international collaboration and completed another species, which is Americana in Brazil. And then the Chinese strain of Asiatica for, again, the HLB citrus strain. And more recently, completed Africana species. So up to date, all the 4 pathogenic bacteria have the completed genome sequencing. So with that sequencing, we are not only provide the important insight of genome evolution on the possible that the genetic basis of a pathogenicity. The genome information also very useful to provide for the useful application, such as detection. For detection here, I just overview those detection. Basically, detection, you can either target the bacteria and target the pathogen, or you can use the host respond. Either way, if this molecular signature is specifically related to the pathogen or disease. In terms of detection, most widely using is PCR, amplified DNA. From starting the invention of PCR machine, that started the conventional PCR gel-based detection, and to the real-time PCR, and more recently, it started using the digital PCR. The digital PCR is different. In series, it's the same as PCR, but the digital PCR is partitioning individual molecule to separate the droplet. So it means the separate, synthesize or amplify each single molecule. So in that sense, that the digital PCR is absolutely quantitation method. In contrast, the real-time PCR is relatively the quantitation. So digital PCR is more accurate in determining the target copy. Another version that the DNA-based testing detection, like a LAMP, which is using the isothermal synthesized process. This is a very sensitive, but in some cases, there's a specificity is the issue. And because the DNA is a complementary double strain, so hybridization can be used with a probe, and a fluorescent label can be used for simple and a quicker way of detection. And the ELISA is another version that using protein basis, and that using the target bacteria or pathogen organism as an antigen, so antibody, the specific recognized. This is a very cost-effective, especially good for large quantity of sample. However, the sensitivity is not as good as DNA basis. because DNA can be amplified. So that's why most popular using the DNA-based detection. Also in some cases using gas chromatography, because the target has a special volatile compound and that can be detected if this compound is specifically related to the disease or a condition. And in fact, for example, in citrus, canker disease have been using dog, sometimes the dog to detect a canker disease, and results show that the accuracy is 95% even better. But more recently, HIV have been proposed that the detection using dog for HIV. But anyway, regardless, whatever the method using, the most time we focus on DNA in ribosomal region, for example. Ribosomal region, the DNA is this region is different in contrast, different to coding region. This is structure protein. The structure protein that is different from translated protein is not necessarily subject to evolutionary selection. So that's a certain variation among these organisms. But because it's very conserved, so the genetic variation at the nucleotide level oftentimes using for molecular taxonomy, because that's sequencing related about the organism. And in addition to that, there's other kind of detection in the region with coding region, where it's a specific gene or protein using as a signature for the design and detection. The non-coding region is often using, such as a simple sequence repeat. Amy just mentioned that. We developed early for this multiple locus sequencing typing or SSR. Either one can be used not only for detection, but also can be used to evaluate genetic variation from the population and individual from population. But regardless of whatever kind of test, here's several criteria you have to take a consideration when you do any kind of detection. Sensitivity. Oftentimes, pathogen is not as high a titer as you expected. So that means that you might have not able to detect a detectable level. So sensitivity is very important. Same as specificity, because it causes confusion if you detect a non-target organism. And then in addition to that, you also need to be quicker, easy, and then reproducible. And the last, of course, is not least, is a cost effect, especially dealing with a large quantity of sample. All of these have to dealing with a fundamental true issue. That is a false positive and a false negative. This is often common and encountered in the diagnosis. Either way, either one you can end up a very cost. I will give you an example later. So I talk about ribosomal DNA-based detection. This is very common and popular use that. But this have some issue. In general speaking, this method is working quite well. For example, currently, the Lee in 2006, he first reported 3 detection methods based on the ribosomal region for this citrus HLB detection. And in 2009, he published another sequencing, the primer based on the solanacearum for detection. In this ribosomal basis detection, he chose the region that the reverse primer are all the same, share common, the sequencing are all common, share same. And so it's same as the Techman probe, also same, all 4. The only difference is a forward primer. What you see here, the primer that in general speaking, the 3' of the sequencing are almost identical, almost. And that's to distinguish each species, and including different species solanacearum. in this detection, in general speaking, working well in a case where you have a reasonable amount of titer of a bacteria. And in a case you don't have a mixed strain in the sample, and you only detect the specific target bacteria, it's fine. But it's had a problem when you either titer of the sample is very low, or you end up with a mixed strain. Because there's a lot of bacteria related to close, even very close to Liberibacter. It may be possible causing such confusion. I give you an example. In 2010, in California, Southern California, it reported that the curry tree had detected HIV positive using the Asiatica primer. And this is a sequencing curry tree, the pathogen we detected. It turned out to be the reverse primer is identical sequencing. And the sequencing tool is identical to the probe. The only difference is a few sequencing region of this, the forward primer. That's the reason why, because the partial match here, PCR, in the process, when primer couldn't find any target sequencing, it might find out some of the related similar sequencing. And that sequence, partial match sequence, can go through the amplifier. Once amplified, this product can be using at the temperature to continue amplify. This end up the product, which is very weak, but it's look like true. And your forward sequencing find that actually that the sequencing almost identical in the region. But we do the more sequencing test beyond that, the cysteine risk, ribosomal region, it turned out to be totally different. So that is causing a problem of this detection, as I mentioned. So for example, this real-time PCR, when you're using each primer specific, working with a target DNA, you get a very nice product, a signal. But this is HIV suspect sample in Southern California. When we tested by those primer, it show up with their CT value at the 33 or even more later. So the reason for that, as I mentioned earlier, because the partial match and that causing the sequencing and the product, the reaction very weak, but later. So this problem is a very continue had the problem several times, and in the detection, and for example in the citrus in Florida, sometimes because the eradication management or HLB, when you find that the sample in the orchard, you got to remove the plant, and then remove the plant, and if this is a false positive, and in some cases even remove whole orchards. So it's very costly. It turned out to be actually false positive. So reliable specific detection is needed. So for example here, so we developed to develop the primer, which carefully select the region where it's specific only to the target, the Liberibacter. And the other word means that select the region where it's a common share in all Liberibacter species, regardless of different strain. However, it's unique to the different species, so that you can specifically detect the species, the targeted species that you're looking for. For example, in this case, we developed a primer which detect the same sample. None of them have any signal turn up even after 40 cycles. So that for Liberibacter detection, one of encountering the problem is early detection, a lower titer. We know all the time Liberibacter either during the early infection, the titer is very low. Not only that the bacteria are lower, but bacteria are unevenly distributed in the hoster. And in solanacearum, the zebra chip disease, as mentioned earlier yesterday, that in the later growing season, even 1 or 2 days before harvest, bacteria being the plant being infected, and you're not able to detect zebra chip bacteria in the tuber. But tuber continue to develop the bacteria titer continue, develop, grow up to become detectable. So that has the common in Liberibacter, the associated disease problem. So improve the specific, not only specificity but sensitivity is needed. So we're also concerned about the genetic variation, because as people are talking about hepatitis or whatever, and as also Liberibacter, since we studied in 2005, and several species being reported that indicating in nature genetic diversity of Liberibacter is much more than we expected. So how these different variation and the strain variation or species, new species, and we have corresponding to a detection, we need to design a primer not only specific, but also in some other cases we're able to distinguish different genetic variation. So for molecular diagnosis, this is the NEST PCR mostly using to increasing the sensitivity of detection. However, NEST PCR had a problem. First of all, NEST PCR had to work in two-run the PCR. That is caused it difficult to, not easy to operate. Also, that this process is likely causing a contamination because you working with amplified products. And to re-amplify and to take a double time cost. So we designed the process which is analog to NEST PCR, but we put all the reaction in one single tube and then one step, the PCR reaction. So this is a problem here, because they here have the two pair primer and working the same reaction. So in order to distinguish that, we have to design a primer in a different temperature, working temperature. In other words, we working with the outer primer with a higher temperature, 10 degrees higher than inner primer. So first run PCR at the temperature where it's only outer primer working because the lower inner primer is too high temperature. And there was a limited amount of outer primer, amount of supply. When they finish the first run PCR, all the outer primer being used up. So that when they started second run and the inner primer and working without the interference by outer primer. By doing so, we are able to conduct the NEST PCR in single tube. And that is showing the sensitivity up to single digital level. And this is the efficiency of test showing that then 99% efficiency. We tested the population in citrus. One is in China population, in the Guangdong population. We showed that in both cases was a standard, and it was compared with the dual NEST PCR showed about more than 10% detection sensitivity. The 10% of the sample being detected positive. Similarly, for standard, we compare the zebra chip sample, where you see here, a standard PCR detected three this sample positive at 28 cycle, but the NEST PCR, single tube NEST PCR, detected at the 21 cycle. And here it's a test negative, but then dual the PCR can detect positive. So that conclude that this single tube PCR indeed increases the specificity, and that is also help to minimize potential positive and potential false positive and false negative. And this detection is easy to work, and it was one single reaction, and including all the cost, additional cost, just outer primer, one pair outer primer. So that is specifically suitable for this the low titer situation. With that, I'm going to stop my talk. Thank you.